All right, real quick, we're just going to kind of go through temperature. That's what we're going to talk about today. Um, basically, we have a picture here, and it says molecules dissolve in the surfaces of different things and undergo a process of outgassing. So gases can be trapped inside of materials, and they get released in the space around them. That's why a brand new car has a new car smell, because the parts that are in the car are made, if there's plastic parts or cloth parts, when they make it and they dye it, because it's brand new, some of the gases that are trapped inside the materials during the manufacturing process, those get released, and that creates that. So in a precision telescope, this can cause some issues. And so this leads to major distortions and contamination. So here we have an image of a NASA engineer who's created some sort of coating to absorb these contaminants. So this image right here is going to absorb these gas contaminants. And so they're just putting this coated panel on the Johnson Space Center's Chamber A of the James Webb Space Telescope. Now on a thermometer, how does the gas get trapped and how does it escape? Well, it boils down to kinetic energy. So everything in the universe is in motion, everything's moving. When you expose it to a warmer atmosphere, it absorbs the heat energy and then it just kind of goes crazy, and so the gas just goes this way. Same thing happens in this alcohol thermometer. This little tube right here has alcohol with red dye in it, and if you increase the temperature of this little tube, the alcohol that's at room temperature just kind of oscillates like this, and then when you add heat to it, it kind of does like this, and it expands. And so there's this very thin tube, okay? And so as the alcohol expands, it's very, very thin tube. The thermometer goes up, and then we mark the different spots, and that's how we could tell somebody's temperature, okay? Another example of this, I got ahead of myself, is this little thing right here. On the old school thermostats that we used to use to set the temperature in a house, basically, and if you ever take one apart, it's kind of neat to see, but there's a metal coil, and the coil has two different types of metal on top of each other. And so basically what happens as the temperature increases, one of these metals will expand faster than the other one, and it causes it to curve. And as it curves, it will actually physically push a switch to turn on your furnace. So this is all due to kinetic energy and temperature. And this is another kind of a neat thing. You don't see these as much. I'm going to show you about the more modern way of taking somebody's temperature. But they used to have these. They were little strips of plastic. You'd hold them on your forehead, and then this would light up when you got closer to your temperature. And basically, each one of these little black things is a liquid crystal. The liquid crystal material is temperature sensitive. So if I put this on my forehead and I didn't have a temperature and it was at 98 degrees, 98.6 degrees, only this image would change color. If my temperature was 100.4 or higher, this would light up. If it was 102 or higher, this would light up. If I had a temperature of 104, this would light up. And same thing though, there's chemicals, and as it gets warmer, they start to move further and further apart. And so that's how you're able to tell the temperature. Now this is the most common looking way to take temperature. Nowadays you buy these, they're not cheap, but they're not too expensive. But now you just zap somebody in the forehead, right? And you take a little device, this isn't the actual thing, but you go boop, and within a second you can find somebody's temperature. But it's the same thing. We kind of shoot an infrared light at something, and then that infrared light bounces back into the device. The device has a thing that can read it. Light has energy, heat has energy. So as the light comes into contact with some sort of heat, and I'm oversimplifying this, when it comes into the heat, the light actually becomes more excited, and so you end up reading more energy than the gun shoots out. Okay, so that's a great way, and these are a little more accurate to measure the temperature of not only your forehead, but also apparently the ventilation systems on an aircraft carrier. So what does this mean? Whoops, let me go back here. So what this means is, I'm going to get rid of my face here. What this means is that we can measure temperatures or the effects of temperature, but really what we're measuring is that kinetic energy or increase of kinetic energy. So there are 3 different scales. Notice that they're all the same. Water freezes at 32 degrees and, Fahrenheit and boils at 212 degrees Fahrenheit. But if you use the Celsius scale, it freezes at 0, boils at 100, that's the Celsius. And then water freezes at 273 degrees Kelvin or boils at 373 degrees Kelvin. And basically Fahrenheit and Celsius and Kelvin, basically 3 different scientists that they created a scale, and they wanted it, it's just a way to kind of measure when things, and water is universal, so it's easy to measure when water freezes, and it's pretty easy to measure when water boils. But this is how the temperatures are the same, it's just the numbers are different. Okay, so then next we have a bunch of equations. You should probably write these down, but these are how you mathematically convert from, say, Celsius to Fahrenheit or Fahrenheit to Celsius, how to convert from Celsius to Kelvin or Kelvin to Celsius. And so in physics we use Kelvin for the most part unless specified otherwise. So we use the metric system. So we tend to use Kelvin. Sometimes we'll use Celsius. It just depends on what you're trying to do. Okay, and so I'm not going to waste a lot of time on this. You could pause here and write these down. These will be posted in Canvas if you need them, and they're also posted in the online textbook. But these are just simple formulas. You plug the numbers in, and that's how you make the conversions. Temperature is also an interesting thing. So here we have thermal imaging of a person, and white, if you look at the scale, is white is the warmest temperature, and dark blue is the coldest temperature. And so really, if dark blue are the cold areas and red to white are the hot areas, what does that tell you? Well, an elevated temperature might be an indication of a malignant tissue or a tumor. So if you look in an area and then all of a sudden there's like a big bright white spot there, they might have a tumor. It just depends. So that's what you're looking for sometimes in thermal energy. Also, a depressed temperature could mean some sort of blood clot or something. So if right here in the middle of the forehead, if somebody had a blue dot like this, if somebody had something like that, well, there's no blood flowing through that space. It might be a blood clot. Okay, that could be dangerous. Or maybe they have a blue spot right here. They could have a blood clot there, so that could be pretty dangerous. And so these abnormalities can be determined just by taking thermal imaging of somebody, which is a little safer than taking an MRI. But it has to be a big difference in temperature. So you'd have to have a big tumor, or you'd have to have a big blood clot. So one last thing before, and I think this is the last slide. An increment on this logarithmic scale indicates the increase by a factor of 10, and thus illustrates the tremendous range of temperatures in nature. I note that the 0 on the logarithmic scale would not occur off the bottom of the page. And so this is the temperature for liquid helium, and this is a logarithmic scale. We don't use this too much. It's just something to see how vast the temperature we can measure. And then really, really hot, and this is temperatures in Kelvin. And so if you see the scientific notation, it's kind of hard to make out. Up here at the top, it's 10 to the 12th Kelvin. And that's experiments in the relativistic heavy ion collider. So nuclear reactions, actually stronger than nuclear reactions, very tiny subatomic particles. And then way down here, we've got 10 to the 0 Kelvin. Remember, 0 Kelvin is absolute zero. So that's when matter stops to move. Now, we've never been able to get that cold, but this is on the magnitude between 0 and 9. We get close, but we can never get 0. So this would be like from 0 to 9 Kelvin. Okay? And then lastly, there's a direct relationship between temperature and pressure. So as the temperature increases, the pressure increases. So as something gets warmer, it can bounce faster, and that creates pressure. But if you have 4 different gases, depending on the gas and the density of the gas, and this is a big thing, the density of the gas, sometimes different gases move faster than others, or they have more space. And so these factors factor into it, but pressure versus temperature pretty much is always going to be the same. If you increase the temperature, you increase the pressure. I should say that the volume is constant, so you almost have to put it in something where the volume doesn't change. Yeah, I'm sorry about my handwriting. My tablet, I need to have IT come in and reconnect my tablet. So the volume is constant, okay, V for volume. So if you leave your volume constant, the pressure will increase. Why? Because it's trapped inside of a container, and the kinetic energy increases. So pressure increases because your kinetic energy also increases as the temperature increases. In other words, they're bouncing off the walls faster. Okay? And that's it.